Okay, so let me do a very quick recap of what we're doing. So we were studying metric properties of Norm spaces. So we started with some properties which presumably are easy to compute, which is uniform smoothness and uniform convexity. And I gave you again just an example of spaces that we care about, which is LP spaces. So an LP space is smooth with a parameter minimum between P and 2, and convex with parameter with exponent and maximum between P and 2. Okay? So these are classical due to Clarkson in the 30s. Then I showed you in the second lecture probably an iteration argument due to Bézier of how this can be boosted, these 2-point inequalities can be boosted to give isomorphism invariant inequalities for martingales with values in an Ivanov space. Actually, so it was an implication. Smoothness implies. Okay, so I just rewrote the same thing twice. Okay, so this has martingale type. Okay, I rewrote the same thing. And martingale cotype. Okay, now we did that. It was true before, but now it's more interesting. So from smoothness and convexity, we can get martingale type and cotype. And then I showed you two different arguments, one due to Christoph of how to boost martingale, not to boost, of how from martingale type one can prove a metric inequality, which is M plus P. And I showed you this argument from our paper of how from martingale cotype you get sharp metric cotype. Okay. So this is what we've done so far. And the easy observation after we worked hard to reach this point is that the moment you have M type R, say, you can get a lower bound for the distortion of the Hamming cube, which is n to the 1 minus 1 over R with the F1 metric. And the moment you have sharp metric cotype S, you can get a lower bound for the distortion of an infinity grid, which is the minimum between n and n to the 1 over S. Okay, and I also mentioned that in the ranges that we cared about, these parameters are sharp. So this distortion can both be attained, but I didn't discuss this. Okay. And a tiny remark. So in the first lecture, I told you that so from amplotype, the right linear notion for amplotype is actually not martingale type, it's Rademacher type. So it's equivalent to Rademacher type. But I argued that okay, for our purposes, there wasn't a huge harm just assuming that the space is martingale type, because in the literature we have 3 examples of spaces between the two. Now, here, for martingale cotype, I mentioned that the situation is much different because L1 has Rademacher cotype 2, but not martingale cotype 2. So here, I can very much argue that there was some harm in this inequality here because the proof I showed you did not capture the case of L1, which for my CS friends is 50% of the interesting Banach spaces, right? So that's not great, but okay, we're going to stick to our choice of just discussing martingale properties. And I owed you one application from cotype before moving on. So are there any questions about this? Okay, so let me just show you a different nonembeddability application, which is going to highlight the importance of the scaling parameter in the inequality. And for this I need a definition, which was introduced by Gromov in geometrical theory. So we say that the metric space MD embeds coarsely into a different metric space. And if there exist two moduli, capital omega and little omega, from 0 infinity to 0 infinity, and the function f from m to n, such that the following holds, such that for every 2 points x and y in the domain, if I want to compute the distance in the image between f of x and f of y, then this is bounded from above by this large modulus, capital omega, of the distance in the pre-inversion. And it's bounded below by this little modulus, little omega of the distance in the pre-inversion. Okay, so far I'm not assuming much, right? The case of bi-Lipschitz embeddings is the case that both little omega and capital omega are linear functions. The case of quasi-isometric embeddings that people care in more geometric settings is the case that little omega and capital omega are affine functions. But here I'm just assuming something very general. Actually, the definition is not over, okay? But let's pause. Have we assumed anything so far? Is this assumption trivial or not?
Lower bound is trivial unless you require that.
Exactly. So the lower bound is potentially trivial. The upper bound is not entirely trivial because I want points which are at distance r to be mapped to points at distance omega of r, right? So I want this function to not take the value infinity. So one assumption, the upper bound doesn't take the value infinity.
Like x to the power of.
Any of them. Or e to the e to the e to the x, and log as a log. And now I'm going to assume something more than the upper bound. I'm going to assume what's called the coarse condition. I'm going to assume that the limit as t goes to infinity of little omega of t is infinity. Okay? So balls of radius r are mapped inside balls of radius capital omega of r, and large distances are mapped uniformly to large distances without caring about the rate. Okay, so it's a very, very weak notion of an embedding. People in group theory care about this because there are some conjectures, topological, some of them, where just the existence of an embedding like this actually is sufficient to prove it. So in some settings, just assuming that such a very weak embedding exists, then this can actually give you reason. Okay, but because it's a very weak notion of an embedding, then most likely, it's very difficult to prove that something does not embed coarse. Well, here's the proposition. If M has sharp metric cotype Q, which is a number in 0 to infinity, not attaining infinity, then I'm going to write something simple, but you can make it more delicate statement, that L infinity does not embed coarsely but it's not really about L infinity, it's about Ls for any S greater than Q. And it's not, I'm never going to use anything infinite dimensional. You can just say, I want all the finite dimensional infinities with just the little omega and the capital omega being independent of the dimension. Okay, so it's not a non-separable argument that I'm not going to take an ultra filter, I'm not going to do it. Okay, so let's see this proof. Okay, so suppose there exists coarse embedding. And you call it capital F from an infinity into M, and then you just also fix N and M such that M being of the order of N to the 1 over 2. Okay, then what I do is that I will, there's going to be the same white lie as yesterday, where you remember cotype was an inequality on the discrete torus. I'm going to identify it with a grid again. Okay, so believe me that this is not a big deal. I will identify Z mod 2m to the n with a grid inside Rm. But I'm going to make a little difference from what I did last time. I have the freedom to choose the side length of the grid. So it's going to be 0, S, 2s, up to 2m minus 1, S, for some scale S, which we're going to fix in a minute. Okay? And then the function little f, which is just the restriction of capital F on, I write z mod 2m, in fact I mean on discrete, which lives inside of infinity, satisfies the metric cotype. Okay, so it satisfies if you remember that the sum as I goes from 1 to n, expectation over x uniform on the torus, dm f of x plus mei f of x, the q is bounded above up to the cotype constant, which I'm not going to care about, by n to the q, expectation over x uniform on the torus and epsilon choice of signs, the distance between f of x plus epsilon and f of x. Okay, and then I'm going to do the usual thing. I'm just going to apply the, not the, yeah.
Because we have s, shouldn't you add ms?
No, this is the addition mod m. So indeed, when I measure the distance,
But f is not even defined. It's defined on this.
it's not. So as I'm saying, this is a white lie. So indeed, when I measure the distance between these 2 points, it's going to be m times s. So far, this is just imagine a bijection between z mod 2m and this grid. Okay, so far, I'm just imagine this as just a bijection.
The factor s also exists on the right-hand side, right? He measures with respect to m in both sides.
So it's gonna, but it doesn't exist here. Here it doesn't exist. This is m, this is just a numerical factor. Okay, and let me just apply the course conditions. And now, the left-hand side, I'm going to bound this from below by the corresponding course condition. So it's going to be expectation over x of the distance in L infinity, and indeed now I have to multiply by s, because now I start speaking about the distance, right? So it's s times x plus mei minus, sorry. We have the course condition, so it's omega plus. It's little omega of s times x plus mei minus x, and this is raised to power q. And what this is here is the L infinity norm of ei, which is just 1, right? So what I have is n times the expectation, sorry, there's no expectation, omega of s. On the other hand, the right-hand side, yes, thank you. The power. The right-hand side, there's an n to the q factor, and here I'm going to have capital omega of, again, the distance between x plus epsilon and x. This is measured in infinity. This is simply s. Right? Omega of s. Right? So let's see, so here it's n times m times s, correct? And here, yeah, okay, it's correct. Okay, so, and now I also have to remember what m was. Okay, actually, no. So this is bounded, this is of the order, because of the assumption of m, of n times omega of s to the q. Okay, so this implies that since this is bound above by that, I can just plug in s equals 1. So I just now remember that I actually don't need this game, so I confused you for no reason. I'm going to plug in s equals 1, but it's still correct. I'm going to get omega of m bound above the capital omega of 1. Okay, this is my conclusion. And m is of the order of n to the 1 over 2, right? So this is omega of a constant times n to the 1 over 2. And this condition was true for every n. So I will send n to infinity. and that's a control. So as you let n go to infinity, this number here is supposed to go to infinity by the course condition, but the other thing which we assume is capital omega just doesn't take the value infinity, so that's it. Now I confuse myself, S can be taken to be 1 from the beginning. I confuse myself because if you want to do R into something for like 2 for R greater than 2, then you actually carry. You need to start with scaling here to make this number here 1. Okay, so, but let's just stare at the argument again. I claim that without having the exactly correct scaling, this doesn't work. Because there was a factor n to the left that came from this sum, and there was a factor n to the q to the right. Okay, so if m was n to the 1 over q times log 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 n, here you would have an additional log 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 n which wouldn't cancel. So you would be able to say, of course, that little omega doesn't grow very much. But you wouldn't be able to say that little omega has to be bounded. Okay, so this is a genuine application of cotype that shows really the importance of the scaling parameter. And for other notions of embeddings, you can apply the same reasoning, and again, the scaling parameter matters again. So that's the end of what I want to say about cotype. Are there any questions? No? Okay, good. So I think we are chapter 6. So
maybe one. Is there a converse to the proposition, like in the Banach space cotype?
This is conditional on Rademacher type being, so okay, if Rademacher cotype was equivalent to sharp metric cotype, then, sorry, you mean for metric spaces in general? You mean for metric spaces or for Banach spaces?
Well, for
Banach spaces, okay, so for Banach spaces, if sharp metric cotype was the same as Rademacher cotype, then this would prove that any space of finite cotype is, because of that, not coarsely universal. So containing everything coarsely would mean that you are forced to have trivial Rademacher cotype, if the implication was true, which would mean that you contain everything linearly. Okay, so if the conjecture was true that the scaling parameter in cotype was always correct, coarse universality, so containing everything with respect to this very good notion, would force you to contain every metric space almost isometrically. So this is part of the reason, this coarse universality conjecture, that people care about proving the sharp Rademacher cotype. Sorry, the sharp metric cotype under space of Rademacher. So for space, there exists that. But indeed, there's a nonlinear Bézier theorem also in the case of general metrics, but only for the case cotype infinity, not for smaller cotypes. This was also the original paper of Banach. Okay, so far we did the expanders, we did the Hamming graph, we did the spaces of bounded length. We didn't say much about them, but we said that martingale arguments work there. And now we did infinity cubes. And both in the Hamming graphs and the infinity cubes, we used very heavily at various points in the proofs the fact that these things are groups. Okay, so in the proof yesterday, there were 3 points at least where I said, okay, as x ranges over the group, x plus something else ranges over the group. So we're doing all sorts of translation invariances left and right. So in the last part, I was torn between two things about what to discuss. So I'll speak about diamond graphs, which are not groups. Diamond graphs, and I guess what we call diamond convexity. That's going to be the name of the invariant. And I should say that everything I'm going to say is joint work with Banach. So everything I'm going to say here is actually it's part of my thesis. The paper is not out, even though it's been a few years. But the paper has expanded a lot. So there's a lot of other applications of this invariant that are in the works, but everything I'm going to say is things that we knew several years ago, and there's a chapter in my thesis for that. I hope it doesn't end up like Kimberly Safra. That's my dream. Yeah. The definition. So let me tell you what the diamond graph is. Well, so it's an iterative, it's a fractal construction of graphs, very, very simple. I just draw it first, and then, so the zeroth diamond graph is just an edge. And then at every step, I take every edge and I replace it for a square. Okay, so first I take my only edge, and I'm going to replace it by a square like this. So this is D1. And then I'm going to go to each of these 4 edges and replace each of them by a square. So we just need some more space. So 4 points. Yeah, I'm not very good at drawing. They're on the board in general. So okay. Could be worse. Okay, so this is the second diamond, and I'm not going to draw it for obvious reasons. So I should say that these objects were very classical. In the context of metric geometry, they originated in some work of Neumann and Rabinovich from 2002. So the diamond graphs decay are constructed iteratively. I'm just going to write what I said in words. So D0 is an edge. And then for every edge UV of decay minus 1, where t is greater than or equal to 1, in the case iteration, we replace it by a 4 cycle. So 4 cycle, which is of the form UAVB. So again, just to be clear, so I take an edge, U and V, this leaves in decay minus 1, and what I do is that I replace it with a square. This now leaves in decay. Clear what the definition is? Okay, now I need one more thing. So if, let me just make sure I phrased it correctly, the pair, I'm going to need a special name for this pair AB, which appeared after breaking an edge in the kth iteration. So the pair AB is called a k-level anti-edge. So this is going to be an anti-edge. So you take an edge, I break it into a square. The two things which are not connected are an anti-edge, and they will denote by AJ of decay all J-level anti-edges of decay for J smaller than. Okay, so what's happening? Let's start with the initial edge up there. I break it into a square. This introduces 2 new points. So at the picture to the right, the top point and the bottom point. And these 2 are going to be recorded as a level 1 anti-edge. And for all the next iterations of the diamond, these 2 points will always be considered an anti-edge of level 1 because these are 2 points this was formed at the first iteration of the diamond. Okay. Now,
So these on the third picture, these are all anti-edges.
so let me erase and then I'll show you. I just need to change the wording. It's easier to show you a picture than talk about it. Okay. So, what are the edges? So let's say that we are in D2. The pair of these 2 points is a level 1 anti-edge, because these 2 points appeared in the first iteration as anti-edges. Now these 2 points, and these 2 points, and these 2 points, and these 2 points are level 2 anti-edges. Okay, so an anti-edge is something that appeared after breaking an edge on the J step. Now let's do some fairly simple counting. So how many edges does the diamond graph have? The K diamond graph? Right. Okay, so we have the edges of the diamond graph for the K. How many jth level anti-edges does the diamond graph have? So each anti-edge is coming from an edge that was broken on the jth iteration. So they are in one-to-one correspondence with the edges of the dj minus 1, right? So it's 4 to the j minus 1. And the more difficult thing is how many vertices does the diamond graph have? No. 2/3. Okay, actually this won't matter very much, it's like 4 to the k, this is over here, but okay. So, and finally one more remark, if I give you a jth level anti-edge of decay, what is the distance on the graph dk between the 2 points A and B? So what is the distance, first of all, in the graph dj? 2. It's 2. Okay, and then for every iteration, you just multiply by 2 because just the 2 points go further and further apart. So it's going to be 2 to the k plus 1 minus j. Okay, so it's not the end of our combinatorics for today, but you see it's manageable. And here's the definition now. So of the metric invariant, so a metric space MD is Q, maybe I should say has diamond convexity Q with constant delta, and this delta I'm going to denote by delta Q of M, so this is going to be the best possible. If for every k in n, every function from the diamond graph into M satisfies the functional equality, so like we've always had, so satisfy the following thing. First on the left I'm going to have a sum over levels from 1 to k. I'm going to have a 1 over 4 to the j minus 1. And then I'm going to have a sum over all anti-edges of level j. And here I'll have the distance between f at the 2 points of the anti-edge, normalized by the actual distance of the endpoints of the anti-edge. Okay, so this is going to be divided by 2 to the k plus 1 and the j to the 2. So before writing the right-hand side, let me just explain what the left-hand side is. I'm summing over anti-edges, and here I have the distance in the image divided by the distance in the pre-image, all raised to the power 2. And what's the factor here? 1 over 4 to the j minus 1 is also the number of anti-edges. So this is an average, and this is a bi-Lipschitz distortion if you want. But I'm just summing this over various levels. Okay. So it has a bit of a feeling of sum over edges on the left, but these are appropriately normalized. And then on the right, it's going to be an honest average over edges for the k, cardinality, and here it's going to be the sum, an edge of the actual finite diamond graph, this definition. So a metric space has a property, has this property, if every function satisfies that. Okay, this is the definition of diamond convexity. I should add a word here. This is for posterity. This is what we call, in the paper there are two definitions. This is what we call graphical diamond convexity. It's far more understandable than the other one in various ways. There's a probabilistic version of that becomes more complicated but useful for other things. But this is the one that we're using. So diamond convexity is going to be this for okay, yes.
So Q is between.
Yeah, so Q is anything between 0 and infinity. Any questions? Good. So let me give you a lemma. You can all prove at home. If M is diamond Q convex, then of course the claim is going to be what always is. The diamond doesn't have it. Then the distortion in M of the K diamond graph is bound below by K to 1 over Q divided by the constant. So, of course, if the metric space was the diamond and F was the identity map, this is not true because all of those distances are 1, so this average is 1, all of those ratios are 1, so this averages are 1, so you have a K factor that shouldn't be that. Okay, so once you check, and the theorem, which I'm gonna prove for you, is that we can completely compute this for norms. So a norm space is diamond Q convex if and only if it has martingale cotype. Okay, so it's an if and only if property of martingales. Actually, the second known characterization of martingale cotype, there's a different one by a property that's called Markov convexity, that's meant to capture the geometry of trees rather than diamond graphs. And I had to make a choice, so I decided to speak about this as kind of a simplification, even though it's more recent. Any questions?
So in that level, so here you have equal weights to each level.
Yes.
And if you can to take only one level, say the top level divided by 2. Do you know that it would destroy the good property of this?
So if you only had one level, only the...
Yeah, but it has in the middle.
I say the middle of. So it depends on how you normalize, right? In the sense that then it wouldn't give you distortion if it were just one summand. But maybe you want to multiply this by k and say you want something. It has to be, for it to be something meaningful, it has to. No, the short answer is I don't know. But I can imagine that you need some kind of symmetry if you. Like,
well, I guess this is developed just to make the proof manageable. Right?
exactly, yeah, exactly.
I just wonder how stable this is after.
Yeah, the short answer is I don't know. I don't know either in one direction or in the other. So we're going to see a bit in the proof where, the varying levels of the diamond are going to play the role of martingale differences. So I'm not entirely sure, or at least not from there. Okay, and let me give you a consequence. So the corollary, which is what Newman two, but of course they proved it without the theorem later, was that the Euclidean distortion of the diamond graph, the Hilbert space, is too convex, is bounded below by square root of k for the k diamond, which I would just do something stupid and say that this is like square root log the size of the vertex. Okay, so now let's go back to the very first lecture, which was a long time ago now. So we said that Bourdieu's embedding theorem tells us that any metric space embeds into Hilbert space with distortion being log the number of points. And we said that actually expanders saturate. So good. But there's a different, also very influential embedding theorem and more an embedding method, which is due to Rao. 98. We said that for specific metric spaces, log can be reduced to square root log. Okay, so any planar graph metric embeds into Hilbert space with distortion at most constant from square root log the size of the group. And the diamond graphs are of course planar. I almost failed to draw them as such, so they are planar. And so this proves that Rao's embedding theorem is short. Okay? And this was not known. So the main point of the paper of Novinovich was to show that Rao's embedding theorem for Euclidean distortion is short. Now, just as a break, I won't even write it. Probably one of my favorite problems in embedding theory is every planar graph embed into L1. Okay, so we don't know this. It's conceivable that whatever metric you can put into a planar graph, what you're going to get is a subspace of L1, is a subset of L1 by Lipschitz.
This is how.
Yeah, very good. In the sense that there was a proof that was claimed at some point it wasn't correct, but basically there don't seem to be any good candidates right now. Okay, so the nonembeddability of the diamond, even for Hilbert space, shows that the Newman-Rabinovich theorem is sharp. And if we have time towards the end, I'll show you one more application to dimensionality reduction. But realistically, I won't have time. So my goal was to prove this theorem up there. So it's again connecting something linear to something nonlinear. And in the case of type and cotype, sort of one direction was very easy, right? So say for a type, you just restrict yourself to a linear function, and you know the inequality just coincides. Now, what is a linear function of the diamond graph? How are you going to start with this inequalities on diamonds and prove something about martingale in this case? Okay. And conversely, it's also not clear how do you use a martingale. I mean, there are natural martingales to use in the diamond graph, so the two directions are different. And how do I want to do it? I think actually I prefer to show you the thing that's new, because the passage from linear, so from martingale cotype to this diamond inequality is actually actually, due to Lee and Naor in 2004, so they have an argument which just works in this case. And what's really new is the converse application, so the converse implication, sorry. So let me prove for you that diamond convexity implies martingale cotype, as it is the case where the nonlinear to linear is actually a difficult direction. Okay? So proof of nonlinear linear, and I'm hoping that I'll get to the other half too, but if I have to do one, I prefer to do this. So what do we have to do? We have to check that the space has martingale cotype too. Okay, so let's start with a martingale. Be it dyadic, I always mean my favorite martingale, where you just flip a corner instead. Be it dyadic x value. Okay, and what I'm going to do, let me just assume that m0 is 0, and I will construct a certain sequence of functions on the vertex of the diamond graph, which are somehow based on this martingale. Okay, so let me do some preliminary work. Which is connecting the diamond with the honeycomb. Okay? So first of all, there's always an issue of language. So we'll construct a labeling one. Can you say again? I didn't hear you.
It's one L in American English.
Perfect. I'm an homage to my 5 years in the US then. So I'm going to construct a labeling of the edges. So it's going to be for the edges of decay, the kth diamond, I'm going to label them by the vector of -1, 1 to the k, and indeed there's going to be repetitions, okay? So as follows. So the label, say at the 0th level of the only edge of the diamond graph is going to be as follows. It's going to be just the empty string, and if we have an edge of dk -1 such that the labeling of the edge, the labeling of the edge is a vector eta, then if I have, this is dk -1, and I've labeled this vector eta of plus -1, I am replacing it by this quadrilateral. Okay, so u and v are still here, left and right, and I'm adding these new points a and b. I'm going to label these two edges as eta, 1, and the other two as eta, -1. So this is eta, 1, eta, 1, comma minus 1, comma minus 1. Okay. I won't write the formula, you understand. Okay, so every time the two, what do you call it, like not consecutive edges have the same label. Okay, and the fact is that it is very simple. So for every label theta, there exists exactly 2 to the k edges on the diagonal graph whose label is theta. Okay, this way I'm replacing labels a lot. Okay. There's 4 to the k edges, 2 to the k edges. Okay, so now I label edges, and now I also want to label anti-edges. So construct a labeling. Notation was not great. So this is going to be LJ program of the jth level anti-edges of dk with vectors of -1, 1 of length j minus 1. So k will not matter here. So the moment something is a jth level anti-edge, it remains a jth level anti-edge forever. Okay? Such that in the picture above, the label of the anti-edge is the label of the edge it came from. Okay, so every anti-edge came from an edge. I just keep the same label. Okay, and I'll claim is it clear?
What's the relation between AB and UV?
They're here. So I have an edge UV on the j minus first,
Right,
and
and
then broke
it becomes anti-edge.
and so then this pair of points that came from the quadrilateral on the other, the two new points.
It is better.
Okay.
Yeah, so there's going to be a thing this time, but theta was the case. Those are my addition. Great, okay. So for every k from 0 to n, there exists a function fk from the vertex set of dk into x, such that a few axioms hold. So first of all, if I restrict, I can always view the diamonds as embedded into one another, right? So every time I'm adding new vertices. So when I say I restrict the function of the kth diamond, the k minus first diamond, you will understand what I mean. The vertices who existed before. Okay? So fk to the vertices of dk minus 1 is equal to fk minus 1. Good. And I have two properties. So property 1 is that if UV is an edge of decay and the label of UV is eta, then Fk of U minus Fk of V is either plus or minus the multiple at this label over 2 to the k. And secondly, if AB is a jth level anti-edge and the label of the anti-edge is some vector omega. Now, eta here is of length k, omega is of length j minus 1. Then the difference between points in the anti-edge is going to be equal to mj omega 1 minus mj omega minus 1 over 2 to the j. And again, I have to put a plus minus because there's no order in the two ends of the anti-edge. Yeah, sorry, it's not very visible. Let me raise the board.
In number 2, you mean A, B, U, V, like on the picture above, or what?
Excuse me, this is a... Yes, thank you. And now it's correct.
So you take the Markov layer and you kind of reproduce it on the diamond.
Exactly, so you find a way to project the diamond onto the cube, but to project somehow the edges on the one side and the anti-edges on the other, so you don't really project the vertices onto the cube in a way that respects, not respects, but that recognizes this marking. Let's see if we... I don't want to do the trick of the one. Okay. It's okay. It's happening. Yeah, it's okay. It's visible. Is the labeling is this clear and clear what we want to do? So the moment you realize that this is what you want to prove, you're actually still, there's only one way to construct functions like that. So at every step, you're really forced to choose the right function by the constraint, and then you have to check. But before that, okay, so the inequality which I want to keep on the board is well, okay. Okay, I want to keep the inequality on the board. So it's here. And let's assume the claim and see why we're finished. Okay, so assuming the claim. What I want to do is that I want to apply the diamond convexity inequality to the last function fn. Okay, and now what is the left-hand side? The left-hand side is a sum as j goes from 1 to n. Yep, k is n now. 1 over 4 to the j minus 1, sum over a and b, an anti-edge of the n. The distance, right, so f of a minus f of b to the q over 2 to the k plus 1 minus q. And now let's go there. F of a minus f of b is mj of omega 1 minus omega minus 1, right? And well, and let's also be a bit careful about that. So as A and B range over the anti-edges of depth j, it's equivalent to having an edge of depth of the j minus first diamond because they are in one-to-one correspondence. And as we said, every label omega is going to appear 2 to the j minus 1 times. Okay, so there's a lot of repetition in the anti-edges. So this 4 to the j minus 1 is going to become 2 to the j minus 1. Okay, so this is going to be the sum. And now I'm going to screw up a constant somewhere, but it's okay. 1 over 2 to the j minus 1. And here I'll have a sum over omega minus 1, 1 to the j minus 1. F of a minus f of b is going to be this martingale difference. q, and it's still, now it was 2 to the k plus 1 minus j, but I multiply this by 2 to the j, so here I'm going to have a 2 to the k plus 1 q, and there's no dependence on j anymore, right? Because when you multiply this by 2 to the jq, things cancel out nicely. Okay, and now again we are in the same situation we've been in before, so we have mj at omega comma 1, mj at omega comma minus 1. This is twice the distance from mj to the midpoint, and the midpoint is mj minus 1. Okay, so this difference, we've used this several times in this course already, is just the marginal increment. So let me just write the answer in the end, and I hope you will believe me. Just need to write it correctly. So this is mj minus 1, okay, times 2. Okay, so here, this is 2 to the q, mj minus 1. So there's going to be a 2 to the q, which is going to cancel with that. So this should be 1 over 2 to the kq, sum over j, when 1 over 2 to the j minus 1, and then there's going to be a sum over omega u minus 1, 1. I just want to do a sum over epsilon in minus 1, 1 to the j, mj of epsilon minus mj minus 1 over epsilon. Q. And now I think when I do this, because I'm conditioning on the last coordinate, I did something twice. So this is going to be a 2 to the j. And anyway, this will not matter too much, but it's what it is. And now this 2 to the j is just a sum over q norms to the power q. Okay, so this is 1 over 2 to the kq. Sum j goes from 1 to n of the marginal difference. Okay, and I'm sorry because I've been doing a mistake. So k has been n throughout. Okay, so k we said is n. We are working on the nth diamond now. That's the k diamond. Okay, so normally that's what we should get. I'm pretty sure that this will be. So we computed the left-hand side of the diamond convexity inequality, and now let's also do the right-hand side. So the right-hand side is 1 over 4 to the n, sum over u and v. Sorry, it's here, okay? So it's the sum over all edges on the nth diamond. And now let's look at the first assumption. By the first assumption, this is just the margin here. But again, I'm multiply counting, right? So for every eta over there, there's 2 to the n edges to which this corresponds. So this 4 to the n has to become a 2 to the n. 1 over 2 to the n. Sum over u and v means, no. Now I just want to do a sum over eta in minus 1, 1 to the n, and now I have to take the qth power of what's there. So this is mn of eta to the q over 2 to the q. And this 1 over 2 to the n times the sum is just an expectation, right? So this is 1 over 2 to the n, q times the lq norm to the power q of mn. And if you compare, I just, there's a delta to the q everywhere, let me just write it too. There's a delta to the q. I just proved that this part is greater than this part, the 2 to the n q cancels, and so this is really marginal.
Won't this work both ways?
Sorry?
So this is the proof in one direction, but here all the quantities are exactly the same, so...
You need to have a completely general martingale.
Because it's a specific case.
Yeah, so if you know, it's kind of a specific function, exactly. I'm not sure that this can be a general function. Yeah, it seems to take a lot of the same values somehow. Okay, so this is the argument. If I'm able to construct this function for you, and let me just know.
So given martingale, we construct this thing, right?
Yeah.
If it wouldn't be martingale.
Yeah, so you're going to see now, I mean, so far I didn't use anything. Sorry, I used here the same claim as usual, but the difference between the two is the increment. But now in the proof you're going to see that only martingale properties come in. Okay, so let me put the claim, and yeah, realistically this can be the end. So, induction. So, F0, there are 0 assumptions on F0, so F0 is 0. And assume Fk minus 1 has been defined. Okay, now I have to construct Fk. Now, the first assumption is that Fk and Fk minus 1 are the same on the previous diagram, right? So consider Fk. So such that, first of all, on the vertex of the previous diagram is just Fk minus 1. And I have to tell you what happens to the new points, right? And if you have an edge uv of dk minus 1, which is replaced, as always, by this quadrilateral uavb replaced by this cross cycle, I just have to define for you what is fk and what is fk of b. Now for the, I can draw the picture. The picture is here. Okay. So I have this UV. I'm replacing it by this quadrilateral UV. And now, what are the constraints that I'm going to put? So I care about what happens. So I know the function here and I know the function here. And I just want to control this difference, this difference, this difference, this difference, and this difference. So I have 2 free variables and need to control 5 constraints. Okay, everything is very linear, so I'm going to define the function at A and B so that these 2 constraints are satisfied, and then the rest are going to be satisfied.
So we have to choose 4 values.
We want to choose 2 values because at U and V it's given,
Okay.
because it should be the same. And we have to satisfy 5 constraints.
It's too many, no?
Yeah, but it's a martingale, so the thing is a martingale, so it has a lot of, how do you call it? It's, the moment you realize what you have to do now is, there's only one way to do it.
Most one.
Just maybe don't erase the constraint.
Thank you. That would have been a very good idea.
Procedure is possible thanks to the fact that we are listing variables.
Yes, completely. Okay, so, okay, save. Okay, so now everything has to come into play. I'm going to define fk of A for you and fk of B. Define the nodes. Okay. So eta is going to be the label of this edge on the k minus first level. And let me just fix this sign. So there's a plus minus in this constraint, right? So I'm going to say this constraint is satisfied for the level k minus 1. So let delta such that fk minus 1 of u minus fk minus 1 of v is equal to delta times mk minus 1 of eta over 2 to the k minus 1. Okay, so such a delta exists. This is the k minus 1. Okay, and then define fk of a to be fk of u. Here there's a choice of plus or minus which matters. So it's going to be minus that sign times mk of eta comma 1 over 2 to the k, and fk of v to be fk of u minus again delta mk eta comma minus 1 over 2. Okay, so I've erased the labelings too. Okay, so now let's check. We need to check 5 constraints. Okay, so we'll check 1. So this was condition 1. This was condition 2. 1 has to be checked for 4 pairs. Now, let's look at the pair u comma a. Fk of a minus fk of u is minus delta, which is a sign, times mk at the point eta comma 1. But remember that if this was labeled eta, this here was the label of eta comma 1, eta comma 1, eta comma minus 1, eta comma minus 1. Okay, so for the pair AU it's satisfied, and for the pair BU, which is down here, indeed you have mk of eta comma minus 1, so again it's satisfied. So for the pairs UA, UB, it's okay by construction. So I mean, I don't need to do anything, that's why I defined it this way. So let's check what happens for the other two. So fk of a minus fk of v, I mean, it's not about the marginal property now, is equal to fk of u minus fk of v, which is equal to fk minus 1 of u minus fk minus 1 of v, since fk is equal to fk minus 1 there, minus delta mk eta comma 1 over 2 k. Now this difference here is equal to delta mk of eta. Okay, so I'm just going to plug in this constraint here. Mk minus 1 of eta, sorry, over 2 to the k minus 1 minus delta mk eta 1 over 2 to the k. And now mk minus 1 of eta is 1/2 times that plus 1/2 times the other. So the factor which is eta comma 1 is going to cancel. Right, so I'm really not doing it's the marginal condition. So it's delta times mk of eta comma minus 1 over 2 to the k. Because it's a marginal property, okay? So it's what it is, and what we have here is eta comma minus 1, which is indeed the label of the edge AV. Okay? And it's exactly the same for the other one, okay? So same for the edge, what we have to show, BV. Okay, it's exactly the same. And now let's just check condition 2 also. So check 2. Let me just look at fk of a minus fk of v. So the fk of u is going to cancel. So it's going to be delta times mk of eta comma minus 1 minus mk of eta comma 1 we're going to do the k. But now A and B is an anti-edge, which is coming from a label eta, so this is exactly what we want to do. So the moment you know what we're going to do, there's one way to do it really. So this is how you construct the functions. And yeah, as Christoph put it, there's a, I mean, this labeling is a way to sort of project the diamond onto a tube, but not project the vertices. That's the important thing. You project edges and you project anti-edges, because that's what's given to you in the inequality. In the inequality, you know something about edges and anti-edges. So, I mean, this proof is clear somehow, okay. It's not a very difficult proof in a way, but I'm wondering if there's some kind of interpretation somehow. In principle, I mean, to go from nonlinear to linear, you want to take the nonlinear inequality, identify some functions as those who, you know, have some linearity in them, have some kind of algebraic structure, and apply it to them. Now, for us, it was these functions which are coming. I mean, here you can write a formula for fk as an alternative sum of some things. I mean, it's just a simple induction.
We should have used somewhere martingale properties of k.
Yeah, sure. So mk minus 1 of eta is equal to mk of eta 1 plus mk of eta minus 1 of eta. And here we don't need, but here we need.
Okay.
Yeah, as I said, it is pretty weird that it is also hard to work in this case from the non-linear to the linear when that should be the easy part. Have you considered the idea of that maybe martingale cotype is not the correct notion, and then maybe there could be another one that's still equivalent to uniform convexity, but you could get to naturally from diamond convexity that's more suited to the diamonds?
Yeah, maybe. Somehow what's happening is that, because okay, I didn't get to that, and I didn't even get to the other direction I wanted, but somehow there's, as we said, many invariants which are being developed, and now we have a phenomenon. There's this invariant which you should think of it as something which captures the geometry of diamonds. Okay? There's a completely different invariant for Markov convexity which captures the geometry of trees. So it's somehow, it was defined by Pimentel and Naor in 2009, but it was already implicit in some papers that were done in the 80s, somehow this kind of inequalities. And they both turn out to be metric characterizations of martingale cotype. So, but at the metric world, they're different. So there are metric space for which the two, you know, one has the one, doesn't have the other. But in the Banach space world, they are all looking the same. So indeed, it's very likely that there is some different notion which is going to make it more apparent, and then there's going to be a different renorming theorem, even in the Banach space.
Yeah, where you could actually take a function that you're suggesting, that a linear function that gives you the inequality for free or something like that.
Yeah, no, I don't know. That's the short answer is I don't know if it can be done. Yeah, possibly. But anyway, I mean, there is some structure here. There's some class of functions which we think of very much as sort of linear because they depend just on the marginal increments in some way. Okay, I wanted to show the other inequality, the linear iteration. It's very nice. Somehow the idea is that, you know, if you want a uniform convexity, true uniform convexity is a 3-point condition. You have the x, you have your y, and you have the midpoint. So you have x, y, x plus y, x minus y. So somehow there's a way that, given your 4 points in a diamond, the iteration, you apply first uniform convexity in this triangle here in some sense, then in that triangle here, you add inequalities up, some Jensen inequality helps you, you get somehow an inequality about points in the diamond, you iterate that and you get that. So you can read the proof. It's one page, it's a very nice iteration. But yeah, anyway, so that's what I wanted to say for that. Hopefully it gives some idea of the flavor of proofs in this kind of math. There's a lot more, but yeah, okay, that's it. Thank you.